very much, Penchang, and well, thank you for organizing this whole series, which I tune into aperiodically, but everything I've tuned into has been great, and it's very good for my students. So it's very good for the students. So thank you for this. And also, anyway, it's a pleasure to talk about this area of research. And there's not that many groups involved in it, but one of the other groups that's involved in it is Penchang's group itself. And so it's not that often that you're invited to give a talk by one of your competitors. But I would say,
friendly competition. Friendly competition.
Yeah, no, that's right. I would say if you're going to be invited by a competitor, you might as well be invited by a gentlemanly competitor. So thank you.
Yeah, sure, yeah.
Anyway, so yes, so what I'm going to be talking about is our work on the cerium-based pyrochlore magnets, which are candidates, very good candidates, I think, for a quantum spin liquid ground state. And I'll be telling you about work that's gone on for, well, about 7 years, actually, to this point. And as a consequence, we've been collaborating with a bunch of other groups who have complementary expertise to the expertise that we have, which is primarily in materials prep and neutron scattering. And so at this point, 7 years down the line, we've got collaborators from about 8 different institutions, which are listed here, and I won't go through them all, but I will say that this is basically what you need if you're going to put together a study that involves material synthesis, crystal growth, theory, low temperature characterization, and neutron scattering. And of course, as usual, we're very grateful to the 3 different laboratories there where we've done our neutron scattering work. Anyway, so I just wanted to acknowledge the collaboration. So I am going to be talking about exotic magnetic ground states and quantum disordered magnetic ground states ultimately, but I thought I should start off talking about conventional magnetic ground states, as this is to be somewhat pedagogical. And so this picture here, this slide here, denotes what conventionally happens when we've got, say, a magnetic insulator with dipole magnetic moments, which decorate some lattice. And if you look at the bottom here, I'm representing the classical dipole magnetic moments as little arrows. And those little arrows we think of as interacting with each other, via some variation on a Heisenberg Hamiltonian, which you see at the bottom, where the energy of interaction just goes like the dot product between near-neighbor spins. And depending on whether J is positive or negative, you can lower the energy either by having near-neighbor spins align parallel to each other, as they do over here on the left, or anti-parallel to near-neighbors, as they do on the right. And of course, that's either ferromagnetism or anti-ferromagnetism, and this will occur at low enough temperatures. And, so what happens as a function of temperature, again, in most conventional materials, is that is represented, here by these 3 plots at the top, which are actually classical Monte Carlo simulations of a 2-dimensional Ising model. So these are spins that can only point up or down, and we can represent, say, the up spins as a black square and the down spins as a white square. And if you're at sufficiently high temperatures, entropy dominates and the system's very disordered. But you still get, small regions of correlated, up spins coexisting with, similar regions of correlated down spins. But the regions of correlated spins get smaller and smaller as you move up to high temperatures. And then at low temperatures, actually, the system is in an energy-dominated long-range ordered state, where you might have some of the minority spin state, which would be the down spins, so the white squares, but it occupies a pretty small volume fraction of the overall material, and so mostly you've got a sea of up spins and a small number of down spins, and as you go to lower and lower temperatures, the volume fraction of the down spins would go away. And then, of course, in between, you've got a phase transition. And, at the phase transition, that's where a symmetry breaking occurs. And, there was nothing in the problem that told you that the black spins should win out over the white spins. So the up spins should win out over the down spins. But in fact, that is what happened here. There's nothing in the problem that told you that. And if you redid the simulation, it might work out the other way. But so there's this clear symmetry breaking, and there's a well-defined phase transition at finite temperature. So that's what normally happens in both ferromagnets and antiferromagnets. And although their structure is different, at least classically, the physics is largely the same, even though you get a different magnetic structure. So anyway, one of the interesting differences, though, between ferromagnetism and antiferromagnetism is that we've known about ferromagnetism for literally millennia, and of course we've actually incorporated it into our technology and navigated with ferromagnetism, going back to 500 BC, 1000 BC, these sorts of times. But antiferromagnetism is very different because there's no net magnetic moment associated with an antiferromagnet. And actually, it was really only discovered and understood with the advent of neutron diffraction. And so this is the discovery paper connected with neutron diffraction and antiferromagnetism. And it's this study by Shull and Smart from 1949. And it shows it's a simple experiment. It's a powder diffraction experiment that you see in the top corner here on the left, where as you cool the system down from room temperature to liquid nitrogen temperature, there's a series of extra Bragg peaks that appear. And in due course, those were interpreted as arising from the ordering of the dipole magnetic moments associated with manganese. Okay. Anyway, all of that only happened in 1949, as a consequence of the development of nuclear reactors and such. But 1949 was the point where you could really study antiferromagnets in a serious way, at least with these relatively simple ordered states. Okay, and something that's kind of amusing and interesting is that actually no sooner had people found out or understood how to study conventional antiferromagnetic states, that they were already speculating about ways to generate an exotic, disordered state at low temperatures. And at least initially, these exotic disordered states were themselves classical in nature. And anyway, I'm just showing you some of the luminary theorists who worked on this problem, very early on, including Gregory Vonnier, who considered antiferromagnetism on a two-dimensional triangular lattice, and discovered that even classically you cannot get an ordered state down to zero temperature. And actually, that was in 1950. Okay, and antiferromagnetism had only been detected in 1949, right? So it didn't take our theory friends very long to understand that there was this interesting connection between antiferromagnetism and certain lattice geometries. And so Phil Anderson, another one of the luminaries with related geometries, has a seminal paper from 1956. Jacques Villain, who's a very famous French physicist, and who sadly just passed away, actually, had many foundational ideas that were developed through the 1970s. And actually, some of these ideas actually predate the discovery of antiferromagnetism. And in fact, we'll come back to this in a couple of minutes. The Linus Pauling was very interested in the structure of ice. And, he understood that, the protons in ice, the hydrogen ions in ice, were not necessarily ordered in all the phases. And so he understood that there was this interesting connection between the structure of ice and, some of these exotic magnetic states. Actually, he didn't express it in those terms, but he understood a lot of the basic ideas. Right. So anyway, I'm going to sort of jump right in to a case study of a particular geometrically frustrated magnet. And it's going to be a magnet that's based on this structure here that you can see over here on the right-hand side. It's referred to as a cubic pyrochlore lattice. And the architecture with which we're going to decorate this lattice, the underlying architecture is that of corner-sharing tetrahedra. Okay, and the significance of the tetrahedra, which you see here, this is one tetrahedron. We're going to put magnetic dipole moments at the vertices of at the four vertices of a single tetrahedron, and then imagine for different combinations of single ion anisotropy and interactions between the moments, we're going to imagine how we can minimize the energy of the system. So this is one particular combination, which might strike you as a little bit contrived, but as I'll explain, it's a situation that actually nature likes. And this is a situation where we've got magnetic moments at the corners of the vertices of the tetrahedra, and actually crystalline electric field effects constrain these moments to point either into or out of the tetrahedra, okay? So the magnetic moments have this easy axis, but the easy axes at the four sublattice positions on a tetrahedron are not parallel to each other. They're not collinear, okay? So the moments couldn't line up. They couldn't be either parallel or anti-parallel, even if they wanted to, okay? And actually, in this model, they do want to be parallel. There's ferromagnetic interactions between the moments. So they would really like to minimize their exchange interaction by aligning parallel, but they can't align parallel because their easy axes are non-collinear. So this is close to a ferromagnet, but it's not quite a ferromagnet. But there is still a magnetization associated with any one tetrahedron. And you can see for this one that I've drawn here, it points from left to right, points this way, okay? But the magnetization associated with the tetrahedron is not 4 times the magnetization associated with one of the moments. And you could convince yourself pretty quickly on the basis of what I've told you that the best any tetrahedron can do is have 2 spins pointing in, 2 spins pointing out of the tetrahedra, okay? And also, you can convince yourself that there are 6 ways to do that. There are 6 ways you can arrange 4 spins pointing either into or out of the tetrahedra to arrange themselves so that 2 are pointing in and 2 are pointing out. So there's a degeneracy of 6 associated with a single tetrahedron. And then you take those tetrahedra and you connect them together in 3-dimensional space with this pyrochlore architecture. And you get a degeneracy that actually scales as some power of the system size. So you get a degeneracy that very quickly gets bigger and bigger and bigger as you make the system size bigger and bigger and bigger. And that's referred to as a macroscopic degeneracy. And it can generate an entropy which is large enough to preclude the formation of an ordered state at low temperatures. There's just too many choices for the spins. And so there's a finite entropy in the ground state, and the state is classically disordered, okay? So that problem, as I've just described it, was first introduced in this paper here in 1997 by Harris Bramwell and co-workers. And actually, this is an experimental study. It's an experimental study of holmium titanate, where it's the holmium 3+ magnetic moments that are arranged on the vertices of the tetrahedron. And they recognized that the disordered state arose because of this combination of ferromagnetic interactions and uniaxial anisotropy. So that's all well and good. And about 10 years went by with the introduction of this sort of problem, which is called the spin ice problem. And I should just mention it's called the spin ice problem because the degeneracy that you have associated with the 2 spins in, 2 spins out on a given tetrahedron, it's the same degeneracy that you have for proton disorder in certain phases as ice. This is the problem that Linus Pauling was working on, connected with ice in the 1930s, and that's why this problem as a whole is called spin ice. okay, which is a great branding exercise, by the way. People really like this term. Anyway, 10 years after the discovery, this group of theorists down here realized that the elementary excitations of spin ice could be described as diffusing magnetic monopoles, okay? And this really attracted a lot of attention. And the idea is actually very simple. We've got a little piece of pyrochlore lattice at the top left-hand corner of this slide. Just two tetrahedra, and they're both in their ground state. So they've both got two spins pointing in, two spins pointing out. And I'm going to, they're classical magnetic dipole moments. I'm going to create a magnetic excitation here the only way I can, and given what I've told you, which is to flip one of these spins. I'm going to flip the spin that's at the vertex that connects the two tetrahedra. And when I do that, I'll make one of the tetrahedra 3 spins in, 1 spin out, and the other one will be 1 spin in, 3 spins out. And so I'll have put defects actually on these 2 neighboring tetrahedra. And the interesting thing is that once that excitation has been formed, once the energy has been put in to flip the spin, then those 2 defects can actually drift away from each other. And this picture in the lower right-hand corner is indicating, 2 of these defects having drifted away from each other. They can drift away from each other and actually separate to either end of the crystal. But once separated, they actually behave like the monopoles that make up a magnetic dipole. Okay, so they interact with each other via some sort of Coulomb interaction. Okay, and they have all the properties of magnetic monopoles as discussed, for example, in high energy physics, such as a string. There's a string of flipped spins that goes between the 2 monopoles, as they pull away from each other, and that plays the role of Dirac strings in high energy physics. So anyway, this generated a lot of interest. The interest was there because it's a classically, it generates a classical microscopic degeneracy or macroscopic degeneracy, sorry. It supports monopole excitations, and those monopole excitations can be deconfined in 3 dimensions. So that generated a lot of interest. Okay.
So let me ask you a question. Does the number of spin matter in this, or it doesn't matter? If you increase, the number of spins from, say half to a very large number, how does this picture change? Yeah,
so that's exactly what I'm going to be getting to. So this problem is the problem that I've been talking about is completely classical. And the problem for holmium titanate and dysprosium titanate, the quantum numbers associated with those states are huge. They correspond to either J equals 8 or J equals, let's see, what would be 15 halves, these sorts of things. So they're very large quantum numbers, and they really are classical. But that's the next thing I'm going to tell you, is that this problem is, and the problem that I've described is that of classical spins on the pyrochlore lattice in the spin ice state. But well, actually, it wasn't even that. It was about 5 years after the original work by Harris and Bramwell, and several years before the work on the classical monopoles, that people started to think about a quantum version of the same problem. So everything that I've been talking about to this point, and even this diagram right here, has these little arrows representing, what would be the magnetic dipole moments. So it's a very classical description that I've been using to this point. But what was introduced, I think, actually in this 2004 paper, but then developed by several different theory groups, over, close to the next 10 years, was the same problem, but just with spin-and-a-half degrees of freedom, and treating the spins as quantum mechanical operators and not as little arrows that interact with each other. And I'm sort of going to, cut to the chase and tell you that the conclusion coming from that was that the quantum version of spin ice, so this is exactly what you're asking about Penchang, actually possesses what's referred to as an emergent quantum electrodynamics. Okay, so the problem actually can be mapped onto the problem of quantum electrodynamics, which is quantum theory of light and matter. And the fundamental ingredients in quantum electrodynamics are magnetic monopoles, electric monopoles, and photons. And those then appear as the elementary excitations in quantum spin ice, okay? So the magnetic monopoles that I was talking about before for classical spin ice, they still survive into quantum spin ice. And these are gapped excitations. In fact, they're the highest energy excitations in the spectrum of excitations for quantum spin ice. There's another set of gapped excitations which are at lower energies that are referred to as bosons and sometimes as electric monopoles. And then finally, there's a set of gapless excitations, which are the emergent photon excitations. Okay, and so these would be, if you like, the magnetic excitations associated with quantum spin ice. And one way to think about where they come from and what is it that's new in the quantum problem that wasn't there in the classical problem. So what there is that's new is the possibility that you can tunnel between ground states in the quantum problem. So in the classical problem, you could create an excitation, but that's not a ground state. That's not a ground state property. You're going from the ground state to some excited state, a state with defects in it. But the quantum problem allows you to tunnel between energetically equivalent but distinct degenerate ground states, like the two little pieces of a pyrochlore lattice that are shown here. So in the top left-hand corner, you've got 4 tetrahedra, each one of which is in its ground state. They've got 2 spins in, 2 spins out, but they're not the same, right? And what's different is that the red spins have all been flipped in the left set compared to the right set, okay? So you can imagine tunneling between these two distinct ground states, but energetically equivalent ground state. And that's what gives rise to this new set of excitations. And the lowest energy excitations are these emergent photons. And so photons, as we all know, have an energy that depends linearly on wave vector, at least at small wave vectors. So they're very much like acoustic phonons, right? Their dispersion relation would look like acoustic phonons, and that's what's represented down in this lower right-hand corner, except that the spectral weight for these emergent photons as measured with neutron scattering, at least in this model, is such that the spectral weight actually goes away as you go to the magnetic zone center, right? It's the exact opposite of acoustic phonons, where the acoustic phonons get stronger and stronger as you go down to the zone center. Okay, so this has generated a lot of interest in the quantum version of spin ice, and it's led to a lot of people wanting to look for quantum disordered versions of these same sorts of problems. Okay, and actually, so that's really where this this study starts. It really starts as an attempt to identify something that's similar to a quantum spin ice, at least a quantum disordered version of one of these highly frustrated quantum spin liquid materials. Anyway, so our attention was first drawn to these cerium pyrochlores with this paper that came out in 2015 from Sabeel et al. It's from the PSI group, which is a very good group. Anyway, so they were studying cerium stannate in powder form. It turns out it's not very easy to make this material in single crystal form, although I'll come back to that at the very end of my talk. Okay, and at any rate, so the main results of their paper are shown here. They're basically doing low temperature magnetic susceptibility and μSR measurements, and essentially all of these are consistent with basically no freezing and no long range order, down to dilution fridge, temperature, so below, of order 20 millikelvin or so. Okay. Now the Curie-Weiss constant that you would get from this is itself pretty low. Okay, this is some measure of the strength of the magnetic interactions. It's about a quarter of a degree Kelvin, but nonetheless, this is the sort of thing that attracts attention. Whenever you see it, because it means that this is at least this has the minimal qualifications to be pursued as a quantum spin liquid type ground state. So this is what attracted our attention. But actually, we didn't initially start studying cerium stannate, and there are two reasons for that. One is that it's not easy to grow. The tin is actually very reactive. Okay, and I hope you recognize this as the periodic table. So we've got the composition of these materials is cerium 2, where cerium is in its 3+ oxidation state, and either zirconium or tin in its 4+ oxidation state, and then oxygen 7. And so cerium is here. It's at the beginning of the rare earth series, right? So cerium 3+ has a 4f1 configuration, and if you use Hund's rule to calculate what the total angular momentum is for 4f1, turns out it's J = 5/2. Okay, so it's right at the opening of the 4f series. And zirconium 4+ and tin 4+ are both non-magnetic, and zirconium 4+ has the electronic configuration of krypton, so it's a filled inert shell configuration, so no magnetism. And tin 4+ is similar, except that it's got a filled 3D shell. Okay, and so we decided to focus on cerium 2, zirconium 2, oxygen 7, because we felt it was likely we could grow single crystals, and this turned out to be correct. Okay, so at any rate, one of the interesting things about this pyrochlore structure is that both the rare earth site, which is shown in blue, and the transition metal site, which is shown in red, they both independently lie on a network of corner-sharing tetrahedra. But because the red network is a non-magnetic network, we're only going to focus on a single so-called pyrochlore network, which is a single network of corner-sharing tetrahedra. And I should just say that I've been involved in studies of the pyrochlores for what seems like forever. I think my first study of the pyrochlores was in around 1990. It wasn't long after my PhD, so that's going way back. And at that time, no one was working on pyrochlores, and no one even, if I started to talk to people about what I was doing, I'd have to go through this rigmarole of telling them about pyrochlores and how they're related to tetrahedra and whatnot. And anyway, that's no longer true. And now there's lots and lots of people working on pyrochlores. But it wasn't always like that. Is what I wanted to say. Anyway, so we've studied many of these rare earth pyrochlores. It turns out this is a very flexible structure. It's also a structure that nature really likes. And so you can, this is a bit of an exaggeration, but you can almost start at the beginning of the rare earth series and go right the way through. And you generate all these, it's a tremendous playground for all sorts of different interesting, quantum physics. There's spin ice physics, classical spin ice physics. I hope I'm going to convince you that there's something akin to quantum spin ice physics. There are metal insulator transitions, all sorts of different things, actually, a very rich system. Anyway, so for better or for worse, we chose to study cerium zirconate and put a lot of effort into synthesizing it. And in due course, we did make materials, and we did a similar set of low temperature characterization to what the PSI people had done on cerium zirconate. And we got similar results. So this is showing you our magnetic susceptibility. Actually, it's the inverse magnetic susceptibility. It's what would be a Curie-Weiss plot as a function of temperature. But you see that, in fact, the inverse magnetic susceptibility is curved. But at this point in the talk, all I really want you to take away from it is that there's no anomaly in the temperature dependence as a function of temperature. Actually, this curvature can be completely described by what's known as the Van Vleck susceptibility, which is shown over here in the top right. And this is the susceptibility that you get, once you know what the crystalline electric field states are, once you know what the energy eigenvalues and eigenvectors are for the crystalline electric field states, which we will get in the next transparency or so. So actually we can account for this curved susceptibility or inverse susceptibility, more or less completely with crystal field analysis. And that's what's shown in red, actually. But interestingly, what we measured in the low temperature heat capacity turned out to be very useful. And actually, these are two measurements on cerium zirconate. So the one in blue is from our group, and the one in red is the one from Pencheng Dai's group. And so completely independent on completely different samples, different people doing measurements in different labs. And actually, the reproducibility is very good, I would say. You can overlay them on an absolute scale, very, very easily. And these were reported within, I think, a week of each other in 2019. And at any rate, it seems like a very consistent story. But the heat capacity, what I really want to draw your attention to is that the heat capacity also shows no signs of an anomaly that would indicate a phase transition. There is a Schottky anomaly, which is here at about 100 millikelvin or maybe 80 millikelvin. There's a peak, and then the heat capacity is falling off as it has to go to zero at T equals 0, and it falls off actually quite abruptly. And we're going to be analyzing the high temperature part of this heat capacity later on. But at any rate, from this, we could see that the Curie-Weiss constant was about minus half a Kelvin, and the paramagnetic moment was relatively small, as expected, about 1.3 mu b, and so forth. Okay, so one of the nice things about studying these particular materials is that they're rare earth-based insulators, and it's not always the case, but it's often the case that there's a very nice separation of energy scales for studying any problem based on rare earth insulators, and my group has studied a fair number of them. And one of the things that's attractive about them is because the rare earth ions lie at the bottom of the periodic table, spin orbit coupling is relatively strong. It's the energy scale is hundreds of millielectron volts. So we know that the Hund's rule ground state is J equals 5/2. So there's 2J plus 1. There's 6 states in that multiplet, and they're separated by the next excited states, the J equals 7.5 spin orbit coupled state, by about 250 millielectron volts. And actually, we can probe that spectroscopically with neutrons, and I'll show you that in the next slide. And then you can sort of step down in energy, and you can look at the splitting between these 3 doublets, right, that make up the J equals 5/2 multiplet. And these are split by crystalline electric field effects, which are weaker than the spin orbit coupling by about a factor of 10. Okay, and here you get splittings between these doublets that are of order 50 MeV or so. Okay, and then finally you get down to what condensed matter physicists are mostly interested in, and that is the inter rare earth ion exchange interactions, which are relatively weak because the rare earth 4F wave functions are relatively localized. And so these tend to be on an energy scale of about 1 MeV, okay? And so actually it's these very low energy scale interactions that interest most physicists, because this is what's really responsible for phase transitions, if there are any, and elementary excitations and such. And I show you, this is a measurement, this is from my own group's much older work on erbium titanate, just showing you spin waves in another rare earth-based pyrochlore. And you can see that the energy scale for these is something less than 1 MeV. So condensed matter physics is low energy physics, so it's not surprising that we tend to focus on this. But actually, we can understand all of this. And understanding all of this actually tells you then about the nature of whatever the degrees of freedom are. Okay, so as it'll turn out in the cerium 3+, there's a pseudospin 1/2 degree of freedom associated with this low energy doublet that is the crystal field ground state. So there's a pseudospin a half, a degree of freedom connected with it, and we can understand the wave function of that pseudospin a half degree of freedom. But we can only do that if we do this high energy spectroscopy first. Okay, so that's actually what we'll do. And so this is just to show you what that looks like. So if we start here at the bottom, in the bottom left, this is essentially raw data of neutron spectroscopy done on powder samples of cerium zirconate, where we're coming in with neutrons that have about 500 MeV of energy. So this is very high energy physics. Okay, and you can see there's these bright spots here around 100 millielectron volts. Those are the highest energy crystal field states associated with the J = 5/2 spin orbit coupled multiplet. Okay, and then there's a gap of close to 200 MeV between that and the lowest energy state associated with the J = 5/2 spin orbit coupled state. Okay, so these aren't terribly easy to see because they're at very high energies, but you can see them, and I've pointed out some of these features in these line scans to the right. But at any rate, this tells us that the J = 7/2 excited state multiplet is about 200 MeV above the J = 5/2 ground state as expected. And then we can do more moderately high energy spectroscopy that actually looks at the transitions from the crystal field ground state multiplet of the J = 5/2 cerium 3+ ion, to its excited states, right? So that multiplet has a degeneracy of 6, and it splits into 3 doublets, as you can see over here in the top right. Okay, and actually, this actually is an eigenvalue problem. And just by looking at the data, you can read off the eigenvalues. The eigenvalues are the energies of the transitions, so they're the splittings, between these doublets. You can just read those off. So the eigenvalues you almost get for free. And then the eigenvectors are the wave functions that describe these pseudospin a half degrees of freedom. And these you get with a combination of looking at the relative intensities between the transition from the ground state to the first excited state and the transition from the ground state to the second excited state, that along with a fit to the Van Vleck susceptibility here, because this depends on knowing the crystal field states as well. Right. So at any rate, all of that is to say that this eigenvalue problem can be solved, to within some accuracy experimentally, and it's all done with neutron scattering. Okay, and in fact, so it tells you what the ground state, what the magnetic moment is in this ground state. Okay, it tells you the wave function, and it turns out that for this particular problem, the wave function associated with this pseudospin a half degree of freedom is very simple. It's just a single, it has a single JZ component to J = 5/2, and that's MJ = ±3/2. So that's very simple and also very high symmetry. Okay, and knowing that, actually, we can look at some of the symmetry properties of this pseudospin a half degree of freedom. Okay, so just by virtue of the fact that you've got a crystal field doublet, which is well separated by about 50 or 60 MeV from the next excited state doublet, which is in turn separated by another 50 or 60 MeV from the highest energy doublet. Okay, just by virtue of the fact that these two states are separated by some large energy gap, okay, to all the other crystal field states, the fact that you've got a degeneracy of 2 here tells you that you've got a pseudospin a half operator that is relevant for whatever the degrees of freedom are that are associated with the cerium 3+. And now, because we know what these wave functions are, we can write down the X, Y, and Z components of the pseudospin a half degree of freedom. And we can look and see how those components behave under the symmetry operations of the point group symmetry at the rare earth site in this structure, and time reversal symmetry. Okay, and it turns out that within this structure, the symmetry operations that are relevant are there's a threefold rotation symmetry as you go along, as you rotate around the Z direction. Okay, that's this C3, and then there's a mirror plane in the plane that contains the local Z axis and one of the symmetry directions within the plane perpendicular to that. So there's a mirror plane and there's this C3 rotation, and each of these X, Y, and Z components of the spin-a-half degree of freedom will behave in a certain way under those symmetry operations. Okay, and actually, what's interesting is that you can classify, any of these rare earth systems which have a crystal field, a ground state doublet that's well separated from the other states, into three groups. Okay, and so the group that we're most familiar with and that we have the most sort of intuition for is the case where we've got an odd number of electrons. Okay, so it obeys Cramer's theorem, and all three components of the pseudospin-a-half degree of freedom, they all behave like magnetic dipoles. Okay, and that's what we would normally draw, and that's the way we would normally think about things. But that's not all there is that's out there. Okay, the other possibilities are you can have also an odd number of electrons, as you have for cerium 3+, but because of the symmetry operations that are relevant to the local geometry, two of the components of the pseudospin-a-half degree of freedom can behave like magnetic dipoles, and the third behaves like a magnetic octupole. And then there's a third possibility, which only comes up when you have an even number of electrons, where one of the components behaves like a magnetic dipole, and two of the components behave like quadrupoles. Okay, so in general, these are the three types of spin-a-half degree of freedom that you can have in these rare earth type systems. And in our case for cerium, it turns out that we've got this dipole octupole spin-a-half degree of freedom. So the way we're going to think about this, it's not that easy to think about because we no longer have these little arrows anymore. But we think of the spin-a-half degree of freedom, decorating the vertices of a tetrahedron, and two of the components we can think of as acting like magnetic dipoles. So they would, so here are some magnetic dipoles that I'm circling with the red and blue, extended regions of magnetization density, for example. So these are behaving like magnetic dipoles, and that's relevant for two of the three components. But for the other third, it behaves like a magnetic octupole, which is shown over here on the far left of this figure. Okay, and for any one of the pseudospin-a-half degrees of freedom, it's the Y component of the spin-a-half degree of freedom that behaves like the octupole, and as you rotate that around to the orthogonal Z component or the orthogonal X component, which isn't shown here, you would get a dipole degree of freedom. Okay, so this, of course, is a cartoon, and it's just meant to give you some idea that that you can have either interacting magnetic dipoles on different sites, or interacting magnetic octupoles on different sites, and it all depends on whether the interaction between the Y component of this spin-a-half degree of freedom is dominant, or whether the interaction between the X and Z components of the spin-a-half degree of freedom are dominant. So there's going to be a whole bunch of different possibilities for the ground states of these materials, but they can either be dominated by their dipolar degrees of freedom or their octupolar degrees of freedom. Okay, so I showed you the high energy physics as determined from neutron scattering. Now I'm going to show you the low energy physics. And it's best to start off down here in the bottom, where I show you energy versus mod Q So this is both powder neutron diffraction or neutron scattering data and single crystal neutron scattering data, which has been angularly averaged. Actually, I think this is all powder data. And you can see that this is a temperature difference data set. It's some low temperature minus 10 Kelvin. And 10 Kelvin is much higher than the Curie-Weiss temperature in the system. So at 10 Kelvin, whatever this is, it's behaving like a paramagnet. And you're subtracting that off. And there's kind of two things that I'd like you to notice here. One is that if you look around zero energy transfer, there's actually essentially no change or there's no growth in the elastic scattering in the zero energy channel that you can see here. And so this is telling us that there's no elastic component to the scattering, and essentially there's no static moment for any of the temperatures that we're studying, which are temperatures above about 60 millikelvin. Of course, there is spectral weight, which is getting enhanced as you go down in temperature, but that spectral weight is all inelastic, and it's between about zero energy and let's call it 0.2 MeV. So we can take this range of energy and integrate that up for our single crystal and look at the Q dependence of this diffuse inelastic scattering. And we get this pattern that you see over here in the top left, which is kind of a snowflake like pattern. I mean, we describe it as a snowflake like pattern, but there's something that looks like a ring around Q equals 0, although it's not an exact ring. And then it has these extensions that go out along OOL directions and out along 111 directions. And actually, it bears some resemblance to the expectations of diffuse scattering in classical spin ice. Okay, so neither the experiment nor any of the theories that we're going to compare to, none of them have any Bragg peaks. They're all very disordered looking structure factors. Okay, so there's no real Bragg peaks. But classical spin ice has, even though all the scattering is diffuse, it's all very blobby in reciprocal space. It has these very interesting features which are called pinch points, which you can see here. And there are regions where these two blobby components of scattering, come together and sort of kiss. And so it's a rather sharp feature, but it's only a sharp feature actually in one dimension. And you see those pinch points in classical spin ice. You see them equally well along the OOL directions and along the HHH directions. And actually the same is true for expectations for quantum spin ice, which are shown over here. Now this is one particular version of quantum spin ice. I'm not going to go into any real detail, but this is actually what you get from integrating over the photon degrees of freedom. And again, there's no sharp features. It kind of looks like classical spin ice, but blobbier. Which might be intuitive as to what you would expect if you took a classical problem and made it quantum mechanical, but you still have pinch points. You still have things that look like pinch points, and we have things that look like pinch points, but they're only along the OOL direction, and they're not that sharp. Actually, they're kind of broad in the OOL direction, right? So they're to the extent that they do they look more like classical spin ice or quantum spin ice? It's probably more like quantum spin ice. But at any rate, there's a lot of similarity to what's the expectations in spin ice problems. Okay, and we can do a more sophisticated version of that same experiment in that we can do that same experiment. We could look at the Q dependence of this diffuse scattering, but we can do it with polarization analysis. And actually, that's what we did using the D7 diffractometer at the Institut Laurier-Langevin, Grenoble. Okay, and then we can also measure this pattern of diffuse scattering, but now we can explicitly measure it only for those neutrons that have been scattered, diffracted with a flip in their spin, and we can separately look at the cross section for those neutrons which were diffracted without a spin flip. And actually, this is an interesting thing to do for a couple of reasons. One of the reasons is that this was one of the experiments that really put classical spin ice on the map This is quite a famous experiment by Tom Fennell and co-workers, published about 13 years ago, where he did exactly the same experiment on, actually, even on the same instrument, on D7, but on holmium titanate rather than cerium zirconate. And holmium titanate has a magnetic dipole moment of about 10 Bohr magnetons. So it's about 8 times bigger than what we have in cerium zirconate. So, the cerium zirconate experiment is frankly quite a bit harder. But nonetheless, there are both interesting similarities and differences. So again, we see only in the spin flip channel, we see this quasi-pinch point in cerium zirconate, but in cerium, in holmium titanate, in the classical spin ice system, it's clear that there's a sharp pinch point, and it's clear that there are sharp pinch points both in the OOL directions and in the HHH directions, and we pretty clearly do not see them in the HHH directions. Okay, and then in the non-spin flip channel, in holmium titanate, they observed what's referred to as zone boundary scattering. So diffuse scattering that follows the FCC Brillouin zone boundaries, which actually are indicated as these sort of honeycombs in gray in the top right-hand panel here. And we actually see the same thing in cerium zirconate. We see diffuse scattering that's extended along these zone boundaries. Okay, so for holmium titanate, this zone boundary scattering is not anticipated in a near-neighbor classical spin ice model. And so it has been ascribed to interactions beyond near-neighbor. And for holmium, because you've got such big moments, you actually expect to have substantial dipolar interactions. And so it's not surprising that you would have the signature of interactions beyond near neighbors in this zone boundary scattering. What is surprising is that we see the same thing in cerium zirconate. Okay, and dipolar interactions are going to be a factor of 64 times weaker in cerium zirconate compared to holmium titanate, but somehow we see the same zone boundary scattering. Anyway, you can see there's interesting similarities and differences between these polarized diffraction patterns in the two cases. So where we would go to from at this point is we would normally go to a measure of the spin waves at low temperatures, either in zero field or in finite field. And then our sort of normal approach is to measure spin waves and model them with linear spin wave theory or something more sophisticated if you have it, and sort of estimate the terms in the microscopic Hamiltonian, and then you can give that to the theorists and they can put it on a phase diagram and so forth. Anyway, that's what we would normally do. And in fact, I've sort of made a living out of doing this over the past 15 years. And here are results from erbium titanate, which actually orders in zero field. So you see nice spin waves even in zero field, but then you can destroy that order and go into a spin polarized state at high fields. And so you can fit these spin waves either in zero field or high field or both. And you can get good estimates for the microscopic Hamiltonian parameters by doing that. And you can do the same thing, and this is just another example from ytterbium titanate. So that's what we would do if we could. But we haven't yet seen any clear evidence for sharp spin waves. We don't see anything like this in the inelastic scattering from cerium zirconate. And I don't think Penchang does either in his studies. Although I don't necessarily want to speak for him.
No, we don't. The data agrees.
Yeah, right, good. So anyway, so this is what we would do if we could do it, but we can't. And so instead, what we do is we get together with our theory friends and we try to analyze the data that we do have. Okay, and so we've gotten together with our theory friends. And this is the underlying microscopic Hamiltonian that's expected for these dipole octupole spin 1/2 degrees of freedom decorating a pyrochlore lattice. Okay, you've got these X, Y, and Z components of the spin 1/2 degree of freedom. It's the Y component which is associated with the octupoles. At least that's the conventional way of describing it. And the phase diagram for this problem, this near-neighbour XYZ Hamiltonian on the pyrochlore lattice, it's been pretty well studied theoretically. And this is what I understand the standard picture to be for, the states that are possible at zero temperature, basically. And because there's 3 terms in the Hamiltonian, the y-axis and the x-axis are different ratios of those parameters. And what's interesting here is that there's a very large parameter space, which are basically 2 different types of quantum spin liquid. There's what's referred to as a pi quantum spin liquid, and so this is pi flux quantum spin liquid and zero flux quantum spin liquid. And these can either be quantum spin liquids which are dominated by the interactions between the octupoles or between the dipoles. So you can see that on this x parameter here at the bottom, it actually separates out along x equals 0, which depends on whether the jy or jx is the bigger of the 2. Right, that's what changes the sign over here. But the point remains that a lot of this phase diagram is occupied by quantum disordered states. Now, the bottom of the phase diagram is not. The bottom of the phase diagram are these, they're non-collinear Néel states. This is a dipolar non-collinear Néel state in red, and this is an octupolar ordered. It's the equivalent of an all-in, all-out state, but for octupoles. That's in this sort of pink on the right-hand side. So that's the phase diagram that's expected. And we get together with these theorists, and we're going to analyze what we can, which is basically the high temperature part of the magnetic heat capacity. Okay. And this is done with what's referred to as a numerical linked cluster calculation. Okay. And so it's a quantum mechanical calculation with finite sizes. And basically, because these measurements are on the heat capacity in zero field, actually, the Hamiltonian that is modeled is not exactly this XYZ Hamiltonian, but it's related to it. It's the XYZ Hamiltonian where the 3 exchange constants are ordered in the order of their magnitude. So they don't model JX, JY, JZ. They model JA, JB, and JC, where JA is the strongest one, JB is the next strongest, and JC is the weakest. Okay, and so the phase diagram that they consider is this phase diagram that's shown over here. Okay, and we've got again ratios of the 3 exchange constants, but they're now related to JA, JB, and JC. And again, you get quantum disordered states for one part of the phase diagram, and then more conventional ordered states for the other part of the phase diagram. Okay, so you can tell which parts of these phase diagrams you're in, but because you've lost the information about which exchange constant is which, you don't know if it's if you get a quantum spin liquid state, say at this position A, you don't know if it's dominated by the octupolar interactions or by the dipolar interactions. And the same is true with the ordered states. But you can get a unique fit or a very good fit to this high temperature part of the heat capacity. Okay, and actually, if you go through this exercise, and I'll give you a reference to show you how to do that, it turns out that the best fit is actually this A parameter. There's actually 2 regions where there are reasonable fits, but for the A parameter, 2 of the 3 exchange parameters are almost the same, and the third is quite a bit weaker. Okay, and so if you go through that exercise, there's actually 2 regions in this phase diagram where you can get a good fit, and those are shown by these sort of bluish bands. And the best fits in each of these bands is at position A and position B. But the best fit overall is at position A. So position A is where we tentatively identify cerium zirconate, and it lies, well within what's referred to as a U1 pi quantum spin liquid. So this is a quantum disordered ground state. This other region here, where we have the secondary minimum, this would give you an ordered state, and the ordered state would be expected to have, there's a variety of reasons why we can discount this, but among other things, it would be expected to give you a phase transition as you lower the temperature. So taken together, this is actually, this is actually, consistent with the original characterization, and that is, there's no evidence for long-range order. There's no evidence for freezing for temperatures above about 80 millikelvin. So this is a bona fide candidate for a quantum disordered quantum spin liquid state. It's not that there's some small Néel moment and you're thinking about that coexisting with a quantum spin liquid state. This appears to be a quantum spin liquid state on its own. We've used this numerical link cluster to fit the high temperature heat capacity and estimate the Hamiltonian. And the net result is that it's strong evidence for this quantum spin liquid ground state. Now, so Pencheng, I can talk a little bit about.
Yeah, sure, please. Yeah, it's very interesting. Yeah.
Okay. So my apologies for running over time.
Yeah. So can I ask a question then? If you go back to the previous slide. Yeah. So A is right on the boundary there.
Right. Yeah.
Does that give you pause that you've left something out?
No. The fact that it's on the boundary is a bit of a fluke. Actually, if I put it on the other phase diagram, it'll make more sense, I think. I'm just going to jump ahead. I jumped too far ahead. So this is the first phase diagram that I showed you, and that boundary there is actually the open triangle here. And what it means is actually the fact that we have these two exchange constants that are almost the same magnitude, that are almost the same strength. It means that it's right at the boundary between, it's definitely a quantum disordered state, but it's right at the boundary between having the octupolar interactions dominate and the dipolar interactions dominate. But it's just the particular point here that it sits on. And so that point is this point here. They're the same point.
No. Okay. All right. Thanks. Yeah.
So there's no special significance to being on the boundary, but it does mean that there's very little, the strength of the octupolar interactions is similar to the strength of the dipolar interactions, if you like. Okay. Yeah. So this is our newest work. Actually, and in fact, sort of accidentally, we only put it on the archive today. We weren't aiming for that. We weren't trying to coordinate it with this talk, but that's just the way it's worked out. And actually, one of the inorganic chemists that we work with, Joe Colas at Clemson, has been also growing pyrochlores, these types of pyrochlores. But he's been doing it by hydrothermal techniques rather than solid state synthesis. So this is very different from what we do. And it has certain advantages in that the growth is at lower temperatures. You're basically growing it out of hot water. That's a bit of an exaggeration, but anyway, but the net result is that it helps with the problem of the volatility of the tin in cerium tin oxide. Okay, and actually we can get small single crystals of cerium tin oxide and powders, and they look very nice. Actually, they don't look like they've been oxidized. They're very green and transparent, and so forth. And we've managed to do essentially a complementary set of measurements, very similar to what we did on cerium zirconate, although not as much neutron scattering. But actually, this is the low temperature heat capacity of cerium stannate from our new hydrothermally grown crystals. And yeah, there are large error bars here, but those error bars are entirely connected with an uncertainty in the mass of the material. So that is that you know, if you can move the whole thing up and down, but you don't move the individual points up and down, if you see what I mean. And of course, this data actually agrees very well with the earlier data by the PSI group, by Sabile et al., that didn't go down to as low a temperature. And all of it is actually very different, surprisingly different from cerium zirconate. You know, it's the onset is at lower temperatures, and the shapes are somewhat different. So it actually, you know, just sort of qualitatively looks different. So so this is all described in detail on this ConMat article. And I'm just going to sort of give you the highlights, because we followed, you know, the same procedure that we followed for cerium zirconate with the same theorists involved. And so the same theorists did the same numerical link cluster expansion, and they could describe the high temperature heat capacity of cerium stannate, or new samples of cerium stannate, very well. So we could get estimates for the microscopic Hamiltonian. And then they can use that, and you know, we could go out and measure the diffuse neutron scattering in cerium stannate. And actually, this is quite interesting. So this is the low Q, what you might think of as magnetic diffuse neutron scattering from cerium stannate, and so as measured in a powder. Okay, and it's a temperature difference measurement. It's 0.3 Kelvin minus 10 Kelvin. So this is the data. And on the basis of the microscopic Hamiltonian estimate that our theory friends get from fitting this high temperature heat capacity data, they can calculate this diffuse scattering, which doesn't agree perfectly, but it actually is a pretty good description of our experiment, you know, even on an absolute scale to within 40%, which I think of as pretty good. But what's actually more interesting, to me at least, is if you look at this magnetic diffuse scattering and you do exactly the same measurement on holmium titanate, which is, you know, the prototypical classical spin ice, you get almost exactly the same diffuse scattering. Okay, it's not as strong. In fact, it's much weaker, but the moment is much weaker. Okay, and but you can see that you can overlay them on each other, and there's actually pretty good agreement. So actually, a lot of what we're seeing in cerium stannate, you know, looks like almost a classical dipolar spin ice state, you know, at the temperatures that we're measuring, which is 0.3 Kelvin.
So when you say diffuse scattering, Bruce, I mean, are you mean that the diffuse scattering with what energy resolution?
Yeah, so it's diffraction, right? So
within 1 millivolt, or?
Yeah, so I mean, the low energy inelastic scattering actually only extends out about 1 millivolt. In fact, it doesn't even extend out 1 millivolt. So, but you're just taking whatever's there, right? You're not doing any energy discrimination in this case.
But the continuum, I mean, that you see, it's include that, right? It's included, right?
Yeah, it includes everything. Yeah, that's right. Okay. And just the same as for holmium titanate, right?
Okay.
So anyway, so this is the you know, so this is the diffuse scattering going out to 8 inverse angstroms. And you know, one of the things that was very interesting about cerium stannate in the literature was, oh, sorry, yeah, okay, I'll come back to that. So at any rate, so we've gone through, I'll go back here. We've gone through this exercise of estimating the microscopic spin Hamiltonian, you know, mostly from the heat capacity, but also using susceptibility data and this diffuse scattering for consistency. And then, you know, we can put cerium stannate on this same plot. And cerium stannate on this same plot comes out down here where this open square is, okay? And so in this region of the phase diagram, if you go to low enough temperatures, you should get a conventional Néel state, okay? It's not a quantum disordered state. It's a conventional Néel state. So actually, if you calculate the heat capacity, you know, based on this analysis, I'm going to go back here, you actually get the calculation that's shown in the inset to this plot in the upper left, okay? And so this plot in the upper left, it shows our heat capacity data. It shows the fit to it in red. And then, the parameters in the Hamiltonian that are extracted then actually give you a phase transition at, very low temperatures, at temperatures like 40 millikelvin, which we don't access in our experiment. And so, the conclusion from the microscopic Hamiltonian that's extracted here is that if you go to low enough temperatures, this system should order, and it should order into what's otherwise a conventional Néel state, and it's the dipole moments that should be ordering. Okay.
Wow.
And so that's because it's being placed in this red region here, and this red region is a dipolar ordered all in, all out ground state. But at the temperatures that we're measuring, which are 0.3 Kelvin, we actually see something that looks like dipolar spin ice. So what we believe we're seeing is a proximate dipolar spin ice above an ordered ground state, which would be dipolar all in, all out. At any rate, where we would place this on this phase diagram is far removed from where, the area where the Sabile et al. Group would place cerium stannate, based on their earlier measurements. And among their earlier measurements were measurements of diffuse scattering at high Q, which were interpreted in terms of, you can see it here, in terms of a quantum liquid of magnetic octupoles. So that actually, this is a very nice paper, very interesting. And I can find no fault with this paper or an analysis, but they report this temperature dependent diffuse scattering at high Q, okay, that they attribute to this liquid of magnetic octupoles. But at least in our new samples of cerium stannate, we do not reproduce that diffuse scattering at high Q. We do have diffuse scattering at low Q, but we don't have diffuse scattering at high Q. Okay, so let's see. No, okay, I'm going to go. So at any rate, in the case of cerium zirconate, we have our work as the open triangles. Actually, there's other work that Pan Chang was involved in, and again, it's work that I can find no fault with. There's a pretty consistent picture that's coming up from these independent studies of cerium zirconate, and it's all consistent with a quantum disordered liquid state that might be akin to quantum spin ice. For cerium stannate, there seems to be quite a significant discrepancy between where these new study places cerium stannate and where the original study placed cerium stannate. So anyway, I think it's clear that there'll be ongoing work on cerium stannate for some period of time, and maybe even on cerium zirconate. But I think there's some level of consensus, at least, on cerium zirconate. So with that, I think I better wrap up, because I better wrap up. So,
yeah, it's extremely interesting. Now it's just very extremely interesting. You should thank thank the guy who did the work for you, right?
Yeah, exactly. That's what I'm doing here. Right. Yeah, so we've got so many collaborators, I can't put up all their pictures. So I thought I'd put up the pictures of the people that could use them.
Right.
Yeah.
Okay. I will ask later, but we'll get Norman to ask first. Yeah.
Oh, you're talking about me, Ping Ching?
Yeah, Mike Norman. Well, you have Norman there. I'm not sure so many Norman.
Bruce, there was a classic study done by Withers a number of years ago, lanthanum zirconate, where they showed pretty convincingly from diffuse scattering, the lanthans actually don't sit on the pyrochlore site. They're sort of distributed in a ring around the pyrochlore sites because they're an underbonded, just sort of typical for this A site in the pyrochlore lattice. So have you guys thought about the role of structural disorder in all of this?
Yeah, yes and no. So we have done the usual things to look at, so we have done powder refinements. And actually, we have done diffuse scattering studies using Corelli, for example, on cerium zirconate. So in principle, we have a lot of data. For the cerium stannate work, there's been a lot of MPDF work done, and there's actually there's been a lot of NPDF, so neutron pair distribution function work, done on both our new hydrothermally grown single crystal and the powders from it, and also on cerium stannate grown from solid state synthesis. And actually, those look clean. Those, things are sitting where they should be, and the bond distances are right, and all the information that you get out of NPDF seems to be consistent. But that's my so actually I've got I wonder if I could show it. I've got a figure that I sometimes show to our students, my students, that just shows, that it could take a long time to come to terms with exactly what's in your crystals, and anyway, it's not beyond the realm of possibility that we don't fully understand our crystals. That's what I would say. So thanks for actually anyway, I'll have to, I wasn't aware of that work, but I'll have to look it up. Yeah.
Yeah, but people are always gonna complain about that, right, Bruce?
Well, as we know, yeah, we all know that.
Andrei?
Yeah, but you have to be a little bit philosophical about it at the end of the day. Right?
Yeah.
Andrei?
I have kind of a related question to that.
Go ahead, Jeff. Go ahead, Jeff. Yeah.
Well, so we studied with Katawaki. We studied the terbium titanate, which is a quadrupole ordering. And you already mentioned that the terbium has two components, a quadrupole, one dipole, and but what we found, or he found, is that the ordering is very sensitive to the oxygen concentration. So really tiny changes in the oxygen concentration can change that. So I was wondering if you have studied that in any systematic way to see the change in the concentration. For example, this extra diffuse scattering in the stannate. That's what.
Yeah. So the answer is yes, actually, that we have, and we're well aware of the Katawaki work on terbium titanate. Terbium titanate is sort of it's a long and interesting story. The different pyrochlores seem to possess somewhat differing amounts of structural disorder, and they can have there can be oxygen deficiency. There can be what's referred to as stuffing, which is that you have the A site on the B site, or vice versa, that sort of thing. Actually, I'm trying to find, this is what I'm doing right now, I'm trying to find an appropriate figure. But in fact, for cerium zirconate, and for all of the light rare earths, and so by the light rare earths, I mean everything out to maybe neodymium or so, the oxidation state doesn't have to be 3+. So the oxidation state here is assumed to be 3+, but that requires perfect stoichiometry. And so if you're looking at, say, a terbium titanate or something like that, the ytterbium is always 3+, right? That's very stable. But if you look at the light rare earths, it isn't. And in the case of cerium, you can get a cerium 3+ or 4+.
Yes.
So and actually, you could measure this in cerium zirconate, at least, by doing a powder X-ray diffraction measurement after you synthesize the material, and you just leave it on the diffractometer for like a week, and you'll see the peaks shift in angle. And so there's an easily measurable despacing, as you acquire more and more cerium 4+ in the system. Now you can go back, you can reduce the material. So this is cerium zirconate, oxidizing in the oxygen of just atmospheric oxygen in the air. And if you anneal the system in a reducing atmosphere, like say hydrogen, for example, or carbon monoxide, you can get it back to, you can get rid of, much of the cerium 4+. Now, as those sorts of defects go, cerium 4+ is relatively benign because cerium 3+ has 1 4f electron, cerium 4+ has 0.
Mhm.
So the defect that you're introducing is actually a magnetic vacancy, which is better or simpler, I guess, than if you were to introduce a different magnetic moment with a different anisotropy and different
Mhm,
couplings
mhm.
and so forth.
Actually,
so-
Bruce has a whole PRB paper talking about this.
Oh yeah,
Mhm.
yeah, that's right. That's right. So there has been a fair bit of work. There has been a fair bit of work done on this, and it's kind of interesting. It's so cerium zirconate in powder form, so I guess when it's got a lot of surface area, can be very sensitive to the atmosphere that it's in contact with. In single crystal form, it seems to be much less sensitive, and things like cerium stannate, cerium hafnate are less sensitive still. So anyway, it's a good question. It's something that we're always worried about, and we're working to control it, but it's hard to control.
Yeah.
Okay, so Andre, and then Igor. Yeah.
Yes, Bruce, Andre here. Thanks for a very insightful talk. I would like to ask you a question about the cerium stannate, the last part.
Yes,
So before I do so, may I make a statement? So I happened to be CC'd on the correspondence between Danielle and Roman, and they were discussing the intricacies of the detail, and me being not an experimentalist, I may be way out of my depth here. So, but the statement coming from Roman, as I recall it, was that their measurement done on HRPT machine, they have a better resolution at high Q. And the argument is something to do with the angle of the Bragg monochromator. You could see that I'm out of my depth here, but his argument.
No, you're
actually
correct. That's exactly the argument.
Yeah, so his argument was that when he takes his crystals and measures this on the wand machine, or wand, however you pronounce it, he gets the same data that doesn't seem to have high Q data. And when he uses on D20 or the HRPT machine, he gets the data that you showed from his Nature Physics paper. Now, I'm not here to defend Roman, but I'm curious, what is your take on this? Do you believe it's the way the crystals were grown, or do you believe this could indeed be with which machine you measured the signal?
Yeah, so I'd say there's two points. So one is that I do think that that our crystals are likely better than their crystals, but that's simply because they were grown at lower temperatures, right? So if you grow at lower temperatures, you're less likely to, you don't introduce the same sort of defects. I mean, that's true. That's true even if you use the same technique and grow at 2 different temperatures. The lower one is usually the one that will have less defects. And here the temperatures are a lot different actually, because in one case it's hydrothermal, and the other case it's solid state synthesis. You're close to the melting temperature, for powders. So his point about his point about the higher resolution being the better way to measure the diffuse scattering, that's not the way diffuse scattering is typically measured. Typically diffuse scattering is measured with low resolution, right? Because you want to integrate over more of reciprocal space in a particular measurement. And it is true that high resolution allows you to isolate the Bragg peaks, so that if you wanted to subtract them out, you could do so. But they should subtract out pretty well anyway, because after all, we're looking at temperature subtractions of data sets that are all, below 10 Kelvin, sort of typically. And so, things like Debye-Waller factors and these sorts of things should be pretty small. Yeah, and so you should be able to. I would say the low resolution measurement is probably the more efficient way to go about it. But that is the disagreement. But I think that disagreement kind of misses, in some ways, the main point. And the main point was, the measurement at high Q doesn't really give us any more information on the microscopic Hamiltonian, anyway. And if I go back to I went through that pretty quickly, but if I go back to where our analysis, places cerium stannate, and this has nothing to do with the diffuse scattering. This is really just a measure of,
The heat capacity.
this is just a description of the high temperature tail of the heat capacity and the temperature dependence of the magnetic susceptibility and the low Q diffuse scattering.
Oh, this was low Q? Because I thought what Benedict, well, I thought what Benedict fitted, didn't you have the plot?
Not
Yes,
the low Q data, low Q
right
data,
there.
low Q data.
But
That's low
8
Q data.
angstrom inverse is still low in this language?
No,
Well,
no.
so this is the low Q. I mean, this is the conventional magnetic scattering, if you like. This is the magnetic scattering that looks like holmium titanate, right?
I see. So you're saying that
So-
the fitting up to about 2 angstrom inverse is what sets those parameters, right? The
Yeah,
tail is
actually,
covered in
so the parameters aren't fit with to the neutron data. There, you generate them, and the same was true for cerium zirconate. You generate them with the fits to the heat capacity and the magnetic susceptibility, and then you compare them to the diffuse neutron scattering to check on consistency. Okay, and so this is what what I'm showing you in the bottom is really a consistency check. Okay, but the point is that if you place cerium stannate in this part of the phase diagram, you don't expect there to be significant diffuse scattering out in that region, and in fact that's consistent with what we measure. So our data set is internally consistent, I would say.
Yeah, I understand.
Okay. Igor?
Okay, yeah, thanks, Bruce, for a great lecture as usual. Couple of questions as usual. So first one is a technical. So is there any idea, do you have any idea about the anisotropy of G factor for this effective spin?
Yes. Yeah. So it's very anisotropic. In fact, there only is a Z component, and the G factor GZ is it's about 2.5, I think. I'm going by memory, and there are no
2.57, yeah.
2.57. Right.
Right,
No,
right. But basically, I mean, you still should, you still could have some, experimental upper limit. I mean, there is no zeros in nature, right?
Yeah.
So what is that upper limit for G?
Well, it's pretty well constrained. I don't have a good snappy answer for you, but it's constrained by both the relative intensities of the crystal field excitations and the fit to the Van Vleck susceptibility.
Right. I mean, maybe ESR should be done, to actually figure that out.
That's a good suggestion, actually.
Because I mean, the question, the difference between 0.1 and 0.01 in terms of GX to JZ ratio, JX to J, the anisotropy of G factor makes huge difference. In neutron scattering, 0.1 is visible, 0.01 is certainly outside, because the intensity that you measure is proportional to G factor squared.
Yeah, right. But I believe this you would take this argument back to what the eigenvectors are of the states that make up the ground state doublet, and so I think if you have only MJ equals plus or minus 3/2, then the other possible non-zero component of G has to be 0.
Right.
Yeah, and actually, the only way to generate something, so if you have MJ equals plus or minus 3/2, that threefold rotation, the symmetry of that threefold rotation means that you've got to skip every third MJ value. So the only other MJ that's allowed for J equals 5/2, so you got MJ equals 5/2, 3/2, 1/2, minus 1/2, minus 3/2, minus 5/2. The only thing you can combine MJ equals 3/2 with is MJ equals minus 3/2. You can't combine it with anything else, because of the symmetry of the point group symmetry. So actually, it's to the extent that you're not getting a significant input from the next highest energy multiplet, I don't know if it's possible to get.
But one way,
value.
But one way, Bruce, you can solve this problem is by turning on the magnetic field, right? Because if you turn on the magnetic field, if your hypothesis is correct, if the dipolar interaction, then you should really see spin waves, right?
Yeah. No, that's a
No,
good
no,
point.
no. You should not see the spin waves if this hypothesis is correct, of course, because you see no spin flip if you have Jx and Jy equals 0. So they are totally dark. However,
actually, the spin. So there's another parameter in the Hamiltonian which I haven't told you about, which actually is related to the effect of the magnetic field, and it's a parameter theta. So at any rate, if theta equals 0, you don't expect to see spin waves, but you can see spin waves if theta is non-zero. So actually, something that I didn't mention for simplicity is that also consistent with our analysis is that this theta factor is close to 0.
I mean, maybe I'm missing something. However, if your effective spin is made of plus minus 3/2, S plus doesn't connect the two states, and so you cannot see any spin wave. That's full stop. I mean, that's why I was asking about the anisotropy of G factor. You can only see spin waves in the to the degree you have Gx, the transverse G factor. But if you say that it is protected, the ground state, the ground doublet of plus minus 3/2 is protected by symmetry, then the intensity of any spin wave will be exactly 0. And by the way, that leads me to my second question or a remark. I mean, I don't like this, and I don't like because I don't understand what is the usefulness of this multipolar terminology. Let me tell you the background. The material I studied and sort of understand is ytterbium-based materials like ytterbium platinum lead, ytterbium aluminum oxide, and this multipolar, the ground state is more or less pure plus minus 7/2, and if I would switch on a multipolar terminology, which some Japanese authors have done, I would be talking about octacosahectapole, which is not useful for selling in the title of Nature Physics, and that's why it hasn't been used anywhere, and successfully so. So I mean, the question, but maybe I'm missing something. I mean, what is the usefulness of this multipolar terminology?
But it's quite general actually, and it's not just the dipole octupole. There's also the quadrupoles that are associated with.
No, I understand. It's a symmetry of the orbital wave function. That's why it is for 7/2 it's octacosahectapole. But I mean, I'm just saying it's not useful
Okay. We're talking.
So I don't think I can do justice to your to your question, Igor, but I do think there are people that can. They might even be on this call. I'm not suggesting that they jump in right now, but there. I mean, the theory actually. This is the language the theory uses.
All right, thank you very much. So the important part of the question was the first one, and you say that it's very interesting that the 0J perpendicular, let's say, is actually protected by the crystal field symmetry.
I'm pretty sure that's right. Yeah.
Thank you very much. Yeah.
Bruce, I wanted to understand. So if that's the case, how come the higher multiplets do have a mixture of five halves and 1/2? Do you see what I'm saying? Like if you had, let's say, whatever rotation, like C3 rotation of the D3D group, I would imagine that if it protects only fixed value of JZ, then there shouldn't be no admixture of 5/2 with 1/2 either.
So the so 5/2 can admix with 1/2, right? Because they're skipping 3. No, sorry, you're right. That is correct, actually. So I'd have to go back and look at this, but you have to skip every second. Every second possible MJ value, right? That's how you get 3/2 can only combine with another 3/2, right? Because you're skipping a half and minus a half.
There's one more question, then I have to go. There's another meeting which I missed out. So actually, Han Yan asked you that. I mean, in the PSI paper, in the PRL paper, they said there was no order down to 60. How do you understand that?
Yeah, so that's a good question. So I'd say there's I sort of have two responses. So one is that it's hard to know that you're at a temperature that's as low as 16 millikelvin.
On a powder. On
on a powder, even on a single crystal, actually. I mean, these are just very hard temperatures to, I mean, the absolute value is tough. But the other thing is that, you know, the theoretical calculation that's been done has been done for this near neighbor only XYZ model, right? And so you get the best description compared to that. And so according to that, you know, you've got this transition to an all in, all out nail state at sufficiently low temperatures. But, you know, if you added in perturbations, you know, perturbations beyond this simple XYZ Hamiltonian, it would almost, you know, this is a pretty weak phase transition. So it's going to be knocked around pretty easily by perturbations. You know, there's a very similar story for, you know, the calculated ground state for holmium titanate, you know, in the presence of dipolar interactions and that. And you know, so Gingrod co-workers, you know, calculated that there actually should be this very low temperature ordered state for classical spin ice, but it's never been observed. So it's not clear if it's never been observed because it's just too hard to cool holmium titanate down to these low temperatures, or because, you know, the real Hamiltonian is just slightly different from the one that was modeled. And, you know, that phase transition can be very sensitive because it's weak, can be very sensitive to these sort of perturbations. So it could be either of those.
That makes sense.
Yeah. Right.
Okay, great. Yeah, thanks a lot, Bruce. Yeah, I really enjoyed the talk. I mean, this is fantastic. You give such a nice introduction that even I understand it.
Well, I think you're kind of an expert, to be honest. But I'm glad you understood. And thanks very much for all the feedback, actually.
Yes,
Yeah.
thank you. Yeah, bye.
Okay, right. Bye-bye.